Welcome to session 8. In this session, we'll continue where we left off from the previous session, problem 4.23. First, we write down the truth table of the circuit that we want to implement. There is an enable input and two inputs. They are asking for a 2 is to 4 line decoder. That means there are two inputs and four outputs. Four outputs are, let's call them D3, D2, D1, D0. When the enable is 0, regardless of the values of x and y, all four output lines must be at 0. When the enable is 1, depending on the input combination xy, we must select one of the output lines. That is the function of a decoder. So when you give the input combination 0 0, it should select the line D0. When you give 0 1, which is binary 1, so this number in binary is the index of the line that is being selected. Of course, it doesn't have to be this way, but this is more intuitive. It's easier to understand. It's just convention, maybe. So 1 0, the second line, and 1 1, the third line must be selected. That that is the truth table of the decoder circuit. Now you can use K-map to simplify the output Boolean expression for D3, D2, D1, zeros, D0. But here you can observe that each of them is only on for one input combination, so you don't need a K-map. You can directly write from the truth table as D3 is simply when E is high and XY both are high. D2 is E X Y complement. D1 is E X complement Y, and D0 is E X complement Y complement. So now we have to implement in the first part using only NOR gates. So the way you do this is, suppose D0 is E X complement Y complement. You can complement this twice. E X complement Y complemented twice will be the same expression. Then the inner complement, this one, can be distributed using the De Morgan's law, and you can write this entire expression as E complement plus xy complement x complement y complement whole complement. So I have just expanded this portion using De Morgan's laws, which is in turn E complement plus x plus y whole complement. Now you can get E complement by connecting all the terminals of an OR gate to E. Then you will get E plus E whole complement, which is nothing but E complement. And then you can use a 3-input NOR gate and give the inputs as E complement x and y, and you will get E complement plus x plus y whole complement. Using NAND gates, you can, this is the expression to get the circuit using NAND gates. You can get x complement and y complement by tying two different NAND gates to tying both inputs of one of the NAND gates to x will give you x complement, tying both to a y will give you y complement, and then you use a 3-input NAND gate to get ex complement y complement whole complement, and then you again do an inversion using one NAND gate. So here, to get D0, the circuit will be using only NOR gates. First you get E complement using one NOR gate, then you use a 3-input NOR gate XY, and this will give you D0. Similarly you can do for D1, D2, D3, and you will get D1 is E complement plus x plus y complement whole complement, D2 is E complement plus x complement plus y whole complement, D3 is E complement plus x complement plus y complement whole complement. And the circuits are similar to this, except that some of these terms, y here x and here both x and y, need to be complemented before feeding into this NOR gate. The second part is using only NAND gates, and for that you have D is E x bar y bar complemented twice. Now you have E. From x you can get x bar by tying both inputs of an AND gate to x. Similarly you can get y complement. Once you have these, you can give them as inputs to a 3-input NAND gate, and then you will have to complement it again, which will give you D0. You can do the same thing for D1, D2, D3. D1 will be Ex bar y whole complemented twice. D2 will be Exy bar complemented twice, and D3 will be Exy complemented twice. So that is how you can implement a decoder circuit using only NOR gates or only NAND gates. We'll go to problem 4.24. It is similar to the binary to decimal decoder that we had earlier, except that a few combinations in BCD are uh, invalid combinations. So here they have allowed us the freedom to take those invalid combinations as don't cares. In decimal there are in BCD there are nine valid input combinations for a single BCD digit, and they represent decimal 0 to 9. So there must be 10 output lines, and depending on the input combination, one of the output lines will be selected. That is, if the input is the BCD number 0, then we will select D0. If it is 1, we will select D1. If it is 2, we'll select D2. 3, you select D3. For BCD4, you select D4. BCD5, you select D5. BCD6, you select D6. BCD7, you select D7. BCD8, you select D8. And BCD9, you select D9. And for the rest of the combinations 10, 11, 12, 13, 14, and 15, these are all don't cares. There are 6 invalid combinations. So in each of the K maps for D0 to D9, there will be 6 X's that you can exploit. Here, when one of the lines is selected, all the other lines must be deselected. So all the other lines must be at 0. So that is the truth table for the BCD to decimal decoder. Now, as usual, you'll either write the expression directly, or if there were no don't cares, if all these had to be 0 for the invalid combinations, then you could directly write the output expression similar to the previous problem. But see, since here there are extra don't care conditions, you'll have to write down the K map for each of D0 to D9 and find out the simplified expression for each of those outputs. I won't do the K map simplification because we already studied that in previous sections, previous sessions, I'll directly give you the results and you can verify whether you get the same results. Then once you have the Boolean expression, it is very simple. Using AND gates and NOT gates, you can get D0 to D9. All these expressions are ANDed and of variables in complemented or uncomplemented form. So you need NOT gates to get the complemented form of the variables, and then AND gates to get the expression itself. So that's all for problem 4.24. We'll see the next problem 4.25. One interesting thing to note in this decoder in any truth table is that we start from 0 0 0 0 and go to 1 1 1 1 1, the number with all zeros and number with all ones. And if you look at the truth table, the first half of the input combinations, if you look at the MSB will be 0, and in the second half the MSB will be 1. Next, within these half blocks, the first half, now you already split this map based on the MSB, then you forget the MSB and look at the remaining variables. Now B will be the MSB of the remaining variables. Now the half map can again be split into two halves, and in the first half B will be 0, second half B will be 1. Same thing in this, the bottom half, for the first half B will be 0 and the second half B will be 1. Again, each of these halves can be split, where C is 0 half the time and 1 half the time, 0 half the time and 1 half the time. So you can keep on going until 0 and 1 alternate between each other. That is a fact that we'll use when constructing larger size circuits using smaller size circuits. So what we need is five to 32 decoder with 5 inputs A, B, C, D, E, and 32 outputs D0 to D31. And when ABCDE is the binary number 0, it should select output D0 should be high and all others should be low. If ABCDE is binary number 1, then D1 must be high and all other lines must be low, and so on. So what you do is you give the first two most significant bits, which are A and B, to a 2 is to 4 decoder. And give the outputs of this decoder as the enable input of a 3 is to 8 decoder. Each of which has 8 output lines. So if you have 4 3 to 8 decoders, you have 32 output lines, which is the number of lines that we actually needed. So at least that checks out. And it's a 3, each of these is a 3 to 8 decoder. To each of these you give the remaining bits CDE. So the inputs to each of these is the same CDE. Now this will be D31, this will be D0, D7, D8 to D15, D16 to D23, D24 to D31. So what happens is similar to what I said before. If A, B are both 1 and 1, then D3 will be selected, and you can see when A, B are both 1 and 1, the numbers you are dealing with, if it was 5 bits, here this is with 4 bits. So if the MSB, two of the MSB bits are both 1, then it is you are dealing with the last 4 numbers in the 16-bit combination. If it's 1 0, then you're dealing with the previous 4. If it's 0 1, you're dealing with these, and if it's 0 0, you're dealing with the first 4 input combinations. So now you can see that the remaining part is the same: 0 0 0 1 1 0 1 1 1 0 1. Remaining part is the same for each of these. So what you do is you have a decoder for each of the remaining bits that will decode to one particular line based on the input at the remaining bits. So we have here four such decoders, and which among these decoders has to be selected depends on the value of A and B. So if AB is 0 0, you select the first decoder. If AB is 0 1, you select the second decoder. So in this way you can get a larger size decoder from smaller size decoders. But if we had to get a circuit for this decoder directly, so we saw in one of the previous in this previous question how what is the boolean expression for the output, and if you are doing it using NAND gates, or let's say you're doing with AND gates, then for each of the outputs you need one AND gate, right? But for if you don't consider the enable pin, then each of the AND gates needs to be a two input AND gate here. That is for the 2 is to 4 decoder. Suppose you had a 3 is to 8 decoder, then each of the you need 8 different outputs, and each of the outputs would need either a 3 input AND gate or two input AND gates. So let's say you have 3 input AND gates and there's no problem with the power consumption and all, then it's fine. If the fan in of the AND gates, you have AND gates such as fan in this 3, then no problem. If you want to get a 5 is to 32 line decoder, then again each of the AND gates you need at the output, you will need only 32 AND gates for that, but each of them will have to be 5 input AND gates. So the fan in of each AND gate must be 5. But here in this situation, if you use 4 decoders like this, you will need 4 AND gates for this first stage and 8 into 4 32 AND gates for the second stage. So you need 36 AND gates, which is more than 32, which is the number of AND gates you would need for direct implementation. But the difference here is you need only 2 input AND gates here and 3 input AND gates here. But if you want to directly implement a 5 to 32 decoder using AND gates, you'll need 5 input AND gates. Or if you'll need more number of AND gates of lesser input, of lesser fan in. Instead of if of a 5 input AND gate, if you have only 3 input AND gates, then for 3 of the inputs you can give 3 inputs to the first AND gate and 2 more to the second stage of AND gate. So if you wanted to have a 5 input AND expression, then you would need two 3 input AND gates. So if assuming you have only 3 input AND gates, if you directly try to implement the 5:32 decoder, then for each of the 32 outputs you would need 2 AND gates, which would mean that you would need 64 AND gates. However, in comparison here you need only 36 AND gates. So we do this type of circuit building where you build larger circuits from smaller circuits so that the fan in and fan out are controllable. You can reduce the number of gates you have to use if you have smaller fan in gates. Of course, if you have AND gates with fan in 5 and you're only concerned with reducing the number of AND gates you want to use, then it is better to directly construct using AND gates instead of doing such a construction. Right, we'll go to problem 4.26. This question is very similar to the previous question, except that instead of a 5:32 decoder, you need only a 4:16 decoder. And instead of using 3:8 decoders, you are allowed to use only 2:4 decoders. It works out because you need only 16 output lines. So you don't need, of course, you can construct with 3:8 decoders also, but this question says we have only 2:4 decoders. So the construction is similar to the previous problem, nothing different. As usual, enable is kept high for the first decoder, or no need, you can use the enable of the first decoder as the enable of the entire circuit, because if the first stage itself doesn't give any output, then sorry, you can't do that. Well, they haven't asked us to construct a 4 is to line decoder with enable, so we'll just leave the enable part as it is for the first decoder. I'll just keep it high. Now the most significant bits of your input AB are given to the first stage, and in the second stage you give CD to all the decoders, and the output of the first decoder is fed as the enable signal for each of the decoders in the second stage. And again, this will be D0, D1, D2, D3, D4, D5, D6, D7, D8, D9, D10, D11, D12, D13, D14, D15. Problem 4.27. From the truth table of the decoder, we can see that depending on the input combination, only one of the lines is high. That means if some min term is high, so each of the input combinations is a min term in a truth table, then one of the lines will be high. So each of the outputs of the decoder can be considered to be a min term. That is, if you have a say 3:8 decoder, and the inputs are ABC, the output first output can be considered to be A bar, C bar, A bar, B bar, C bar, because the first line is only high when A is 0, B is 0, and C is 0. So it is the min term M0. Similarly, this is min term M1, M2, M3, M4, M5, M6, and M7. So the decoder is actually giving you the min terms as it out, all the min terms at once, the value of all the min terms. So it would be very simple to implement F1 is equal to summation of midterms 146. You would just need an OR gate, right, between the outputs 1, 4, and 6 of the decoder. Only problem here is that they have asked us to implement it using only NAND gates or AND gates. And to get an OR gate using only NAND gates, you would need 3 NAND gates. But they've also asked us to minimize the number of inputs at the external gates. So there's a better way to do it with a smaller number of input terminals, inputs in the external gates. And that is to use a active low output 3:8 decoder. And it's active low, what you will get is the complement of each of these. So now what do you do? F1 of ABC is sigma 146, which is the complement of sigma 23, or let me see. F1 is sigma of 146, which is nothing but A bar B bar C plus A B bar C bar plus ABC prime. This can be written as, using De Morgan's laws, in this way, which is nothing but M1 prime, M4 prime, M6 prime complement. So similarly, F2 is M3 prime, M5 prime complement, and F3 is M2 prime, M4 prime, M6 prime, M7 prime complement. Now each of these you can get using a NAND gate. This is a 3 to 8 decoder with the inputs ABC. To get F1 you have to NAND the complement of 1, 4 and 6. So take 1, 4, 6, NAND them and you will get F1. For F2 it's 3 and 5. So take 3 and 5, NAND them you will get F2. F3 is 2, 4, 6, 7. 2, 4, 6 and 7 NANDed together to give you a F3. So that is how you can get the three functions that you need using a 3 to 8 decoder. So any 3 input function, 3 input Boolean expression can be realized using a 3 to 8 decoder and external NAND gates. Problem 4.28. I'll leave this question as a homework. All you need to do is the same thing as the previous problem. Use 3 to 8 decoder and the outputs, which are the main terms. And here they have said you can use any external gate, so you don't need to use NAND gates. You can use an OR gate. So you don't need an active low decoder. You can use an active high decoder, and then simply get the OR of the minterms that you need. Only difference here is that the expression doesn't have only minterms. It has other product terms, which you can convert to minterms. So you have to convert the expression to its canonical sum of products form. and then from there you can easily add the minterms using an OR gate. You usually OR the minterms using an OR gate, and follow the same thing that we did in problem 4.27 to get the desired outputs. So I'll leave this as a homework problem, and we'll move on to problem 4.29. Give me a minute. Problem 4.29 is a slight modification of an existing circuit. So you must have studied priority encoders already. Only difference here is that D3 is the lowest priority and D0 is the highest priority. So if all the inputs are 0, then outputs are don't care, we don't care. and V is just a control output, not a control output. V is just an output that tells you whether one of the lines has been selected or not, if there is an actual output input or not. If there is no input, that is if all of them are 0 0, then V just is 0 and you can tell that there is no input at your circuit. In all other cases, V is 1. So if D3 is selected and if D3 is high and all others are 0, then your output is 1 1. If D2 is high, regardless of the value of D3, output is 1 0. If D1 is high, regardless of the value of D2 and D3, output is 0 1. If D0 is high, regardless of the value of D1, D2, D3, the output is 0 0. From this truth table, you can write K-maps for this question. Let me draw the K-map also. For X, this is the K-map. For Y, this is the K-map. For X, you can form a quad. For Y, you can form two quads. And the output expression is simply X is D0 prime D1 prime, Y is D0 prime D1 plus D0 prime D2 prime. V is simply D0 plus D1 plus D2 plus D3. That is X. That is why. And that is V. Alright. Problem 4.30. Specify the truth table of an octal to binary priority encoder. Provide an output V to indicate that at least one of the inputs is present. The input with the highest subscript number has the highest priority. What will be the value of the four outputs if inputs D2 and D6 are 1 at the same time? In octal to binary, only 7 input lines are present because there are 8 input lines are present because there are only 8 single digit octal numbers, or there are only 8 octal digits. D0 to D7. Let the binary outputs be X, Y, Z, and we have the output V. If all of them are 0, then V is 0 and we don't care about X, Y, and Z. Let me write the subscript in the reverse order, which is standard. Now the priority is to the input with the highest subscript. So D7 has the highest priority. That is the truth table of an octal to binary priority encoder with highest priority given to the input with the highest subscript, along with an output V that indicates whether at least one of the inputs is present. Coming to the second part of the question, what will be the value of the four outputs if input D2 and D6 are 1 at the same time? One of the inputs is 1, so V will be 1. V is 0 only if all inputs are 0. Next, we have to look at XYZ. 6 has a higher subscript number compared to 2, so D6 and D2 are on at the same time would mean that priority is given to D6, so XYZ will be 1, 1 and 0. Okay, we are more than halfway through, so I'll take a small break and come back later.